Please turn your notes to 6-2, Multiplying and Dividing Radical Expressions. Today we're going to be finding the products and quotients with radicals, as well as simplifying radical expressions. This will be very similar to our exponent practice at the beginning of this chapter. A couple of reminders while you're getting your notes ready. Make sure you're wearing your headphones. Make sure you're taking your own notes. Remember that you are able to pause the video at any time, rewind the video at any time. Let's go ahead and get started. First, I'd like to go over these problems that you worked on for your exit slip yesterday, just as a quick reminder before we get started. So this one says, the first question, find all the real square roots of each number. Real square roots. What does square roots mean? That's 2. Okay, so the square root, the real square root of 25, that's 5. Okay, the real square root of 0.16, that's 0.4. And the real square root of negative 64, we can't do, no solution, because it's a negative number. Next, we're just going to work on simplifying this radical expression. If you remember me telling you so, we're going to take the square root of each thing individually, splitting them up. The square root of 9 is 3. The square root of b squared is b. Okay, we can also write them as fractions so that you can divide each individually, like so. And then it turns out into a to the 8 divided by 2, which is a to the 4th, and b to the 18 divided by 2, which is b to the 9th. Okay? Last one here, cubed root of each piece that we have here. So the cubed root of negative 125, that is negative 5. And the cubed root of a cubed is just a. So your answer here would be negative 5a. So go ahead and check over your answers from last time. If you needed any refreshers, here we have them. Okay, 0.4 this should be, not just 0.4. All right, let's move on to some new stuff. Recalling just our simple formula or methods for solving these types of things, if you have parentheses and an exponent out front, each term inside the parentheses gets that exponent. Okay? Also, we can move backwards. So if both of these have the same exponent, we can move them inside two parentheses and give them the same exponent. Okay? Similarly, for this next one, we have the root is the same. This is sort of new. So we're going to have this same root underneath the radical sign, and then we can move both of those and multiply them underneath. Okay, so this is a little bit new. We're going to look at some examples here. Same exponent. Okay, so 2 squared, 3 squared, that becomes 2 times 3 squared. These two here are just like this one. 4 cubed, 5 cubed. Remember, this only works if it has the same exponent. Then 4 times 5 goes in the parentheses and you cube them. However, if you have the same index or same root, which will be like this is like the square root of 2 and the square root of 3. Those can both be moved under the radical sign, multiplied, so the square root of 2 times 3. Similarly, with the cubed root of 4 times the cubed root of 5, we're going to be doing the cubed root of 4 times 5. Please be sure that you're only using this technique when they are being multiplied together, which means we're not going to use this when we are adding and subtracting, just multiplying. Okay, so the first thing we're going to work on is just putting this to work, all right? So we're going to look at a few examples using this new formula, you might say, to do these problems. Can you simplify the product? Explain. Okay, here we have a cubed root, and here we have a square, or a root of the 2. Let me see if I can make it so that you can actually see it. This is a square root. Okay, it's not going to let me. Sorry, everyone. This is a square root here. So since they are not the same roots, the answer is no. We can't simplify this any further, only if they are the same roots. Here we have a cubed and a cubed, so we definitely can simplify that. The answer is yes. Let's go ahead and do that. So it becomes the cubed root of -4 times 2, which equals the cubed root of -8, which we know we can solve to be -2. That would be our answer. Okay, let's look down at the second letter A. You have a 4 and you have a 5. Those roots are not equal, so we cannot solve this. We can't simplify it. However, we have the 5th root here and the 5th root here, so we definitely can solve that. Make them one big 5th root. So we have -5 times -2 underneath the radical sign, which becomes the 5th root of 10. We can't take the 5th root of 10, so that's going to be our simplest form, just like that. Remember on the previous problem how I said we couldn't go any further. We couldn't take the square root or the 5th root of 10, so we just left it as so. Okay, we're going to apply that method to all of the problems that we're doing. We have to leave our answers in simplest radical form. That means that if we can take out a square root or a cubed root from underneath the radical, we are going to do that. So let's look at these examples. Square root of 24. Do we know of any perfect squares that fit into the square root of 24? We do. This equals the square root of 4 times the square root of 6. This is why it's going to be very helpful for you guys to have that chart that we made the other day in front of you while you're doing these problems. It's also going to be helpful to try and memorize them because you won't be getting these charts on your tests or quizzes. Okay? So, square root of 4 we know is 2. We cannot take the square root of 6, so we're going to leave that underneath the radical sign, and that's going to be our final answer. We can do the same thing here for the cubed root. Okay? So, do we know of any perfect cubes that 24 can be divided by? The answer is yes, we do. We can take the cubed root of 8, we know that's a perfect cube, times the cubed root of 3. The cubed root of 8 is 2, and we can't take the cubed root of 3, so we're going to leave that underneath the radical sign, and that is our answer in simplest radical form. Notice this prompt here. It's going to be more efficient if you know your perfect squares and cubes. You can also use a factor tree, okay? So it's going to be easier for you if you start memorizing those things, but if you don't, we could have looked at the factors of 24. We know that 2 times 12, let me write that a little bit. Okay, so I went ahead and wrote all of the factors of 24. 1 times 24, 2 times 12, 3 times 8, and 4 times 6. Now that we know all the factors of 24, we can go ahead and look. Are any of these perfect cubes? Yes, we know that 8 is a perfect cube. So that's the method you can use if you don't have them memorized. Okay, so let's work on a few examples using our simplifying methods now. Okay, so our little prompt here says it might be helpful to group by our radicand or by the index. So what this means is we're going to take each piece that's underneath and separate it first so that we can work on them separately. So this means we're going to take the cubed root of 54 times the cubed root of x to the 5th. So let's see here. We can take, what's 54 divided by perfect cubes? How about 27? The cubed root of 27 and the cubed root of 2. And let's see, how about the cubed root of x to the 5th? Well, this means that we can take 3 of those x's out, so that will be, okay, let me show you here. We can do x cubed times x, whoops, x cubed times x squared here. We can split that up any way we want, so that becomes the cubed root of, or the cubed root of x to the 3rd power can just be x, or x to the 1st power, and this x squared has to stay under. Okay, so we have, let's move this information to the right. We now have the cubed root of 27 from over here is 3. We also have the square root of, or the cubed root of 2 left over. Okay. Sorry, it's going to be a little difficult to write here, guys. And then we have this x to the 1st and the cubed root of x squared. So we have in total 3x on the outside of the radicand, and underneath the cubed root radicand we still have a 2x squared. Okay, we'll do a couple more of these in case you got lost along the way here. This is going to be our method. Okay, there would be your final answer in simplest radical form. So let's move on to the next one here. We're going to take the numbers separate from the letters, remember. So the cubed root of 128 times the cubed root of, let's split up that x to the 7th right away. We know that x cubed can go in there. How many times can we take an x cubed out of x to the 7th? Twice. 2x cubed and an x to the 1st. If you are confused as to how we're getting this, we're going to look at this radical and see how many groups of 3 can we take out of this 7. So x cubed, and x to the 1st. That's 2 groups of x cubed, and then we have x to the 1st left over. All right, so let's work on this 128 here. Can we take cubed roots out of there at all? I'm thinking the answer is yes. We can take out the cubed root of 64 times the cubed root of 2. Okay, the cubed root of 64 is 4. How many groups of x? Remember, there was 2 groups of x, so that's x squared out front. The cubed root has to stay. What do we have left over? Well, we have this 2 that we couldn't take out, and this x to the 1st that we couldn't take out. So our final answer is 4x squared times the cubed root of 2x, or 2x to the 1st, if that helps you. Okay, let's get working on our next example here. Again, we have a cubed root. Lots of cubed roots going on here. If I can write on my paper. Hello. Oh, there we go. Cubed root. What can 32 be separated into? Perfect cubes. How about 8 times 4? Because we know that the cubed root of 8 is 2. And then we leave the cubed root of 4 underneath the radical sign. Also, then we have to work on these a's. The cubed root of, how many groups of 3 can fit in to 8? 1 group, 2 groups, 3 plus 3, that's 6. What's left over? 8 minus 6, that's 2. So we have 2 that we took out, 2 groups of a cubed, so that's a squared. Left under the cubed root radical, we have a 4a squared. Okay? Separate your numbers from your letters, but when you're all said and done, you have to put them back together. Last example here. Now we're working with the squared root of 200 a to the 6th, b to the 7th. So what can we separate 200 in that's a perfect square? How about 100 times 2? So this becomes, what's the square root of 100? 10 times the square root of 2. And then our letters here, we have a to the 6th. How many groups of 2 can we make out of that? 1, 2, 3. 2, 4, 6. Okay? Similarly with the b, we have the square root. How many groups of 2 can we make out of 7? Well, hopefully 3. 2, 4. If I can make my pen work. 2, 4, 6. And 1 left over, b to the 1st. All right. So, on the outside of our radical, we have 10. How many groups of 2 can we make out of a? That's 3 groups, no leftovers. How many groups of b of 2 can we make? Well, that's 3 groups as well, b squareds, with 1 left over. So let's go back under our square root. The numbers that we have left underneath, that's 2 and 1b, so b to the 1st. So our final answer then, 10a cubed b cubed, 2b to the 1st underneath that square root. All right. I want you to take a moment and pause the recording and try these 3 on your own to see if you can do it before we move on, just like we did last time. Okay, for those of you who are either done with your problems or decided not to pause the video for whatever reason, I am going to get started on these examples. You should have split 81 into the cubed root of 27 times the cubed root of 3, which gives you 3 times the cubed root of 3. Okay, and then this x cubed, cubed root of x cubed, whoops, cubed root of x cubed, not the cubed root of 3, excuse me. Those 3's can just divide out and equal x, or x to the 1st. Right, so we get 3x to the 1st times the cubed root of 3 in simplest form. Good job if you got that one right. Okay, now we're going to move over to the next one to the right, which is a 4th root. So the 4th root is going to split into 64. 4th root of 16 times the 4th root of 4. Can we take any groups out of x cubed that are 4? No, I don't think that we can. So we have to leave that x to the 3rd underneath. How about the y to the 6th? We can make one group of 4, and what's left over is a group of 2. Perfect. So let's simplify this then. The 4th root of 16, we get 2. What else can we take out for sure? 4th root of 4 has to stay. 4th root of x cubed has to stay. This y section can split up into y to the 1st and the 4th root of y squared. So let's put that all together. What's outside the radical? 2y to the 1st And what's underneath the radical still is 4x cubed y squared. Okay, so that would be your answer in simplest form. Last one here. First, we're going to put these two together. Since we know they have the same root, we're going to put them underneath. 4 times 16 is 64. So now we have the cubed root of 64. Well, we can solve that. That equals 4. Simple as that. A couple more examples of simplifying the product. What we're going to do here is a little more complex than the ones prior. Okay, so pay very close attention because I can't be there to help you when I'm done. So let me move this one out of the way. I might need a little more room. What we're going to do first, instead of combining first, we know that we're taking the square root of both of these things. Square root, okay? We are going to separate our numbers into perfect squares before we get started, because if we combine them first, we're just going to have this giant number to work with. So what do we know 72 can divide by or into that is a perfect square? How about 36? Okay, so let's change this one into 36 times 2 times x squared. Remember, we're going to put these letters into things that are perfect squares here. And y squared is already a perfect square, so we're going to leave that. Okay? So this is completely factored underneath. How about the next one? We have the square root of, well, we don't have any perfect squares here, but let's write it as 2 times 5 for the sake of just doing it for me quick. Let me fix this. 2 times 5. X to the first can't be simplified. Y cubed can be simplified into y squared, y to the first. Okay? Again, we're taking the square root here, so we want to make perfect square groups. All right? Now we're going to do this, combine. Let's combine these things. So this becomes a square root of 36 times 2 times 2 times 5 times x squared times x times x times y squared times y squared times y. Whew, that's a long problem, but we are going to get through it. Okay, so now what we're going to do is look at things that are similar and pair them into squares. Do you see where I'm talking about here? So this will become square root of 36 times 2 squared, which is 4, times 5 times x squared times x squared times y squared times y squared times y. All right. Now let's work on taking those square roots. Okay. Square root of 36, we know we can do. That's 6. Square root of 2 squared, that's 2. Square root of 5 has to stay. Square root of x squared is x. Square root of this x squared is x. Square root of this y squared is y. Square root of this y squared is y. And this y has to stay. So what's staying underneath? 5y. Now let's just do some cleaning up. We get 6 times 2 is 12. X times x is x squared. Y times y is y squared. And the square root of 5y stays. Now this is kind of a lot of work, but the process will go faster once you get the hang of it, all right? Let me show you on this next problem. Whoops. Let me show you on this next problem a little faster way to do this, okay? So what do we know we can take out of both 45 and 35? How about a 5, okay? So let's take out a 5, we have 9 left. Take out a 5, we have 7 left. So let's put this 5 right out front. We know we can take it out of both square roots, so we can just pull it out front, okay? Do we know the square root of 9? We do. That's 3, so we're going to take that out too. 7 has to stay under the radical sign because it's not a square root. There's no other numbers to combine it with. Okay? Now let's look at our letters. We have x to the 5th and x. That's x to the 6th power. Can we take the square root of that? We absolutely can. That makes 3 groups of x squared, right? X squared plus x squared plus x squared, or times, that's 2 plus 2 plus 2 is 6. So we know we can take x cubed out because there's 3 groups of x squared. How about the y's? We have y to the 7th here. Can't we take out y to the 6th times y to the 1st? So we know that that's 3 groups, and the y stays under. Okay, this process was a lot shorter, but if you weren't following properly, you might want to rewind and see where I did this stuff. If not, you should follow the same process that we did up top. Separate things, take out similar things, and then simplify, if that's more your style of solving. Okay, so this is 2 different styles of solving. One is quicker, but you could also make a lot more mistakes that way. Why don't we go ahead and simplify this, as I noticed that I didn't. What's 5 times 3? That's 15. Okay, 15 x cubed, y cubed, times the square root of 7y. So there is your final answer. Everything up until this point was dealing with simplifying and multiplying. Now we're going to deal with division or fractions, okay? So it's going to be different but similar, all right? Division, quotients. If, again, we looked at this property, the nth root of A and the nth root of B are real numbers. B can't equal 0 because, remember my shirt, can't have 0 in the denominator. Then they can both go under the radical. Okay, so the nth root of A divided by the nth root of B can become 1 nth root under the radical A divided by B. So let's work on that. First example is the square root of 18, x to the 5th, over the square root of 2x to the 3rd. Let's put that under one radical. So we get the square root of 18x to the 5th over 2x cubed. We are going to simplify within first. What is 18 divided by 2? That's 9. And remember, when we're dividing exponents, we are going to subtract. So 5 minus 3, we get x squared. We can take the square root of both of these things. This becomes 3x to the 1st. Good. Letter B. We have both the cubed roots, so we are going to put them under one big happy cube root. We get 162y to the 5th power over 3y squared. 162 divided by 3 is going to be 54. And again, we're going to subtract the exponents. Y to the 5th minus y squared is y cubed. So we can take the cubed root of 54 4, we know what that is. It's actually not a cubed root, but it can separate into something that is. So we can get the cubed root of 27 out of here. And we are left with the cubed root of 2 times the cubed root of y cubed. So we get 3y times the cubed root of 2. So really it's very similar to multiplication, except what you're doing is simplifying under the radical first and then taking the roots. Okay? Next slide. I want you to try this one on your own. Take a moment, pause the video, and let's check your understanding. For those of you who have chosen not to pause the video, I'm unsure why, but we will continue. The square root, okay, both of these are square roots, so we can combine underneath 50x to the 6th over 2x to the 4th, which will give us the square root of 25x squared. 50 divided by 2 is 25. X to the 6th over x to the 4th simplifies to x squared, which we know the square root of 25 is 5, and the square root of x squared is x. Good job if you got it correct. Nice work. Let's move on. One more example here, divide and simplify. Same idea. Square root of 21x to the 10th over 7x to the 5th. Let's divide the numbers. So we get 21 divided by 7 is 3. X to the 10th divided by x to the 5th is x to the 5th. Remember, we're subtracting exponents. So how many groups of 2 can we take out of x to the 5th? X squared, and x to the 1st. Well, we can take out 1, 2 groups. So we get x squared. The number this time is going to stay underneath, and we have 1x left over. There's your final answer. One last little thing to look at here before we are finishing up with our lesson. Error analysis. We are going to be doing a worksheet very similar to this when I return. Explain the error in this simplification of radical expressions. Looks like we started out with the 7th root of x to the 5th over the 4th root of x to the 2nd power, or x squared. This student decided to take 7 minus 4 and bring it outside. Where is the error here? Remember, you cannot simplify unless these two things are the same. If we had 2 7s or 2 4s, we definitely could have combined like they did, but since they are not equal, this is already in simplest form. We cannot go any further. Okay, this is going to conclude our lesson. There will be no exit slip today. So, get to work on your worksheet. There are 2 of them. One will be simplifying and one will be multiplication and division. So, thank you for watching and doing your homework, and I will look forward to seeing you on Monday. One more video for the week. Thank you. Bye-bye.